Hey there, deep divers, ready to ride the tide? Because today we're diving into the awesomely weird world of tides. And trust me, this isn't just about the moon pulling some water around. By the end of this deep dive, you'll be able to impress everyone with your tidal knowledge, and you might even see these powerful forces at play across the entire universe.
Absolutely. We've got some seriously cool research here that busts some common myths and dives deep into the science behind tides.
Okay, so let's get this tide rolling. You know how we always hear that high tide happens when the moon is directly overhead? Well, get ready to have your mind blown, because that's not exactly true.
Yeah, that's a common misconception. Our source explains that there's actually about a 12-minute delay. The highest tide actually hits a little bit after the moon has passed its highest point in the sky.
A 12-minute delay? Seriously, what's the ocean waiting for?
Think of it like this. Imagine you're swinging a ball on a string. The ball doesn't reach its highest point when your hand is directly overhead, right? There's a slight delay because of the momentum and the forces at play. Well, the Earth and the Moon have their own little gravitational dance going on, and that's what causes the delay in the tides.
So it's all about the physics. That makes sense. But speaking of gravity, this source says that both the moon and the sun play a role in the tides. Now that blew my mind. I mean, the sun is huge GE. You'd think it would just totally dominate this whole tide thing.
It's true. The sun's a gravitational powerhouse. But you're forgetting one crucial thing. Distance. The moon might be the little sibling in this equation, but it's way closer to Earth. And that proximity gives it a surprising amount of gravitational pull. In fact, the moon is responsible for about 68% of the tidal forces we experience here on Earth.
So even though the sun could totally win in a cosmic arm wrestling match, the moon sneaks in and steals the show when it comes to tides.
Exactly. It's like trying to move a mountain. You can yell at it all day, but if you want to make a real impact, you've got to get up close and personal. And here's where it gets really wild. We get tidal bulges on both sides of the Earth. There's one facing the moon, that one we all know and love. But there's another one directly opposite it.
Wait, hold up. How is that even possible? How can there be a bulge on the side of the Earth that's farthest away from the moon? That sounds like some serious water-bending magic.
It all comes down to those differences in gravitational pull that we're talking about. The moon's pull is strongest on the side of Earth that's closest to it, so that creates the bulge that we'd expect. But here's the thing. The moon is also tugging on the Earth itself. It's pulling the entire planet a bit closer, you see.
So the entire Earth is getting pulled towards the moon, even if it's just a tiny bit.
Precisely. And on the opposite side of the Earth, the water isn't being pulled as strongly as the Earth itself is being pulled toward the moon.
Yes.
So it's like the water is lagging behind, which creates that second bulge.
Wow. I'm never going to look at a high tide the same way again. There's so much more going on than meets the eye. But wait, there's more. Right. This source mentions something called land tides. Are you telling me that the ground beneath our feet is also moving because of the moon's gravity?
That's exactly what I'm saying. The Earth isn't a perfectly rigid sphere. The land itself experiences these very slight bulges as well, almost like the Earth is breathing in and out.
So are we talking about massive earthquakes here? Should I be worried about getting seasick from standing on dry land?
Don't worry, you won't need your sea legs for this one.
Yeah.
These land tides are incredibly small. We're talking about a difference of about 16 inches. And they happen over such a vast area, and it's such a slow pace that we don't even notice them.
So we're all just bobbing up and down on the Earth's crest without even realizing it. I love it. That's both hilarious and strangely comforting. It's like the Earth is doing this slow, gentle dance to the moon's tune.
And it highlights a crucial point.
Mm-hmm.
These tidal forces aren't just limited to our planet. Remember, it's all about that difference in gravitational pull across an object.
Wait a minute. Are you saying there are tides in space? Okay, now you've officially blown my mind. Tell me more.
That's right. Tides in space are definitely a thing. And it gets even wilder when you start thinking about objects with immense gravity, like black holes. These are like the ultimate tide makers.
Oh, man, here we go. You're going to mention spaghettification, aren't you?
Yeah.
I'm both terrified and weirdly fascinated by that word.
I can't resist. It's just too perfect of an example. Basically, if something gets too close to a black hole, the difference in gravitational pull between one end of that object, let's say a spaceship for dramatic effect, and the other end is so extreme that it gets stretched out like, well, you guessed it, spaghetti.
Okay, I definitely need to see a diagram of that because my brain can barely handle the visual. I think I get the point. It's the same principle we've been talking about with the tides here on Earth, just cranked up to 11, right?
You got it. Black holes take these tidal forces to a whole other level of intensity, but the underlying concept is the same. It's all about the difference in gravitational pull across an object. And speaking of extreme cases, our source material dives into this fascinating example, the story of Mars and its moon, Phobos.
Oh, yeah, Phobos. I was wondering when we were going to get to that. Our source mentioned something about this moon having a date with destiny.
Let's just say it's not going to end well for Phobos. You see, this little moon is slowly but surely getting closer and closer to Mars because of the tidal interactions between them. And eventually, Phobos is going to cross an invisible line called the Roche limit.
Roche limit. Okay, you've piqued my curiosity. What is that?
Imagine a game of tug-of-war, but instead of two teams, it's the gravitational forces of Mars battling it out with the internal gravity holding Phobos together. The Roche limit is the point of no return, where Mars's gravity wins and Phobos, well, Phobos gets ripped apart.
Wait, seriously, Mars is going to shred its own moon. That's brutal. So what happens to all the pieces? Does Mars just get a cool new asteroid belt?
Some of the debris will likely rain down on Mars, but here's the really cool part. Scientists believe that some of those pieces might actually form temporary rings around Mars, much like the rings we see around Saturn.
Whoa, are you serious? Mars might get rings. That's
Mhm.
incredible. Though I guess I probably shouldn't plan a vacation to Phobos anytime soon.
Probably not. But hey, it's pretty amazing to think that something as seemingly simple as a high tide here on Earth is connected to these mind-blowing cosmic events, right?
Absolutely. My understanding of the universe just got a whole lot bigger and a little bit more chaotic.
And it makes you wonder, what other subtle effects are we missing in our everyday lives? What seemingly small forces might actually be shaping our world in ways we don't even realize?
It really makes you think, huh?
It really does.
So to recap for everyone listening, we've learned that tides are more than just the moon pushing water around,
Right.
although it's a big part of it. The sun's gravity plays a role too, even though it's so far away. And get this, there are tides on land, tides in space, and even tides strong enough to rip a moon to shreds.
And don't forget that 12-minute delay shows you the ocean doesn't always run on time.
That's right. But that just makes it even cooler. It all comes back to gravity, and the closer you are, the stronger the pull.
Yeah, and that's not just some abstract physics concept either. The difference in gravitational pull across an object is a fundamental force that shapes the universe, from the ocean tides to the way planets and moons interact.
That's a really good point. It makes you wonder what other hidden connections are out there, what other small forces are shaping our world that we don't even realize.
That's what makes exploration so amazing. There's always something new to discover.
Well said. A huge thank you to our expert for joining us today and shining a light on this awesome hidden world of tides. And to all you deep divers listening, thank you so much for joining us on this journey. If you want to learn even more, be sure to check out the source material for this episode. And until next time, keep those brains curious because you never know what you might discover on the deep dive.